Okay, I want to talk a little bit more about potential and potential energy. So if I have two charges here, then they're going to have experience a force. They're going to create a force on each other. That force is going to want to push them away from each other. As such, there is some potential energy associated with these guys just hanging out next to each other. We've talked about that idea a fair amount. Now I want to present some equations for that. So the potential energy of 2 point charges hanging out next to each other. Well, why do they have energy associated with that? Well, because I have to do work in order to bring them together. And how much work do I have to do? Well, it depends on how far apart they are, right? If they're very far apart, then how much energy does it take to move them a little bit? Oh, not that much. As they get closer, every inch that I move them closer together requires more and more energy, as shown in this slide. We see that if I'm way out here and I'm trying to move this positive charge towards this other positive charge, if I'm way out here, moving it this distance only takes a small amount of energy. Whereas moving it that same distance when I'm close requires more work and therefore stores more potential energy. And so the equation for the potential energy of 2 point charges hanging out next to each other looks like this. It's a fairly straightforward equation. Remember that energy is not a vector. However, it can be positive or negative. So, whereas with our electric field and our Coulomb's law equations, we were careful to always use the absolute value of our charges, in this case, we don't want to do that. In this case, we want to use the signs of the charges, because two like charges will have positive potential energy, indicating that they want to get away from each other. However, a positive and a negative will have negative potential energy, indicating that they want to go together. So we have to be careful, and we use the signs on the charges when we're talking about potential energy and when we're using the equation for potential that I'll show in just a minute. So what do we have here? We've just got two charges. Here we're calling them Q and Q prime. We could call them Q1 and Q2, or QA and QB. It's just two charges. Here's K. Remember that K can be written as 8.99 times 10 to the ninth, or it can be written as 1 over 4 pi epsilon naught. So 1 over 4 pi epsilon naught is the same as K. And notice the r is not squared in this case. However, r is not the radius of whatever round thing I give you. It is the separation between Q and Q prime. So in the case where they have opposite signs, the charges, like I said, we have negative potential energy because they want to come together. And so that's kind of interesting. We can write the potential of a point charge using that same equation. Recall that when we very first started off talking about potential, we talked about potential as this thing of like, well, what would the potential energy be if I put a charge there? There's not one here. But if I did, what would its potential energy be? That's sort of how we introduced potential. So we sort of introduced potential as taking the potential energy and dividing away the charge that might be there. We introduced potential by just finding the potential energy of a charge at a location, and when we divided away that charge, then we were left with just the potential. And so we can do that same thing. We take this equation here, and we divide out Q prime, and we just end up with the potential. And so we see here that potential is a straightforward equation, and it's not a vector. That's a big part of why we talk about potential in these electrical situations, is because it's not a vector. And the mathematics for things that aren't vectors is just easier. As anyone that's working on the quiz this week can probably tell me, right? It's tricky. Vectors are just tricky. And potential is not a vector quantity. But it still contains all that same information about the electric field, because we know the electric field points from high potential to low potential. So it's kind of cool that we get the information about the vector without having to do the mathematics of the vector. What can we say here? Only the source appears in this expression. So that's an important point here. The source creates the electric potential around it, right? So here's a question for you. If there is only one charge in the entire universe, this is the only charge in the universe, is there any potential energy associated with this? The answer is no. If there's only one charge in the entire universe, then that charge has no potential energy, because potential energy is an interaction with its surroundings. If I bring another charge in, now these two have some potential energy because of their interaction. One charge in the universe experiences no force and has no potential energy. However, if there's only one charge in the entire universe, is there any potential? The answer is yes. This creates potential which surrounds the space. Everywhere around it, it creates a potential. Is there an electric field? Yeah, there's also an electric field. So if there's only one charge in the entire universe, then that charge surrounds itself with the electric field and it creates a potential all around it. Those can exist with just one charge, but we cannot have any forces or any potential energy if there's only one charge in the universe. For that, we need at least two charges. Also note that this expression works for a point charge or any spherically symmetric charge. So a lot of times we talk about point charges, and by point charge we mean it has no spatial extent. But I also refer to things like this as a charge. So any spherically symmetric ball of charge, this also works. In that case, that R is how far am I from the center, right? In general, R is how far am I from the charge. If I'm talking about some spherically symmetric ball of charge, then it's how far am I from the center of that charge. Okay, so I have a couple of examples here. I have a couple of clicker questions first, and then a couple of numerical examples. Rank in order from largest to smallest the electric potentials at the numbered points. 1, 2, and 3. Why don't you pause the video, think about it, and I'll see you on the other side. Okay, well, in order to analyze this, we're going to want to use our equation for the potential due to a point charge. Notice it is proportional to the charge and inversely proportional to the distance from that charge. Notice that points 1 and 2 are the same distance from this charge, so they have the same potential. So I'd want to look over here for somewhere where 1 and 2 were equal. So definitely either C or D. As I get farther from the positive charge, the potential goes down, so 3 is smaller. So 1 equals 2 is bigger than 3. Ding, ding, ding. Winner, winner, chicken dinner. Okay, how about this one? Now we're going to have a negative charge. How does that change things? Let's rank in order from largest to smallest the electric potentials at the numbered points. Now, in this case, again, 1 and 2 are the same distance, and so they should definitely be equal. So I think we're still limited to either C or D. But is 3 at a higher potential or a lower potential than 2 is? Well, let's remember that negative charges make holes in our electrical landscape. So if I was to plot potential versus some distance from a negative charge, and so if we had some negative charge right here, what would the potential look like? Well, in our electrical landscape, negative charges make valleys. And so it's way down here, and it looks something like that. Right? Remember, this is a negative sign. And so this is my plot of the potential due to a negative charge. Notice point 2 might be something like here, and point 3 then might be right here. Okay, so we see here that both 2 and 3 are negative, but which is at a higher potential? Well, 3 is at the higher potential. And so we see that for the negative charge, the correct ranking is 3 is at a higher potential, 2 and 1 are equal. Okay, let's put some numbers on it. What is the electric potential 1 centimeter from a 1 nanocoulomb charge? And what is the potential difference between a point 1 centimeter away and a second point 3 centimeters away? Okay, so we're just going to apply our equation for the potential due to a point charge. And this is fairly straightforward. We can kind of just crank through it. We'll just plug in our numbers. So, K, I'm going to round that to 9. Our charge is 1 times 10 to the negative 9th coulombs. And in this case, we are 1 centimeter away. 1 centimeter is 0.01 meters. And so I run my calculator and I get 900 volts. So that's a reasonable value. How about the second part of this question? What is the potential difference between a point 1 centimeter away and a second point 3 centimeters away? Well, let's see here. Let's do some proportional thinking, shall we? Our potential at 1 centimeter was 900 volts. If we triple R, what happens to V? If we triple R, V must go down by a factor of 3. So we have a potential of 900 volts at 1 centimeter. The potential must be 300 volts at 3 centimeters. What is the change from 900 volts to 300 volts? When I say potential difference, I mean, what is the change in potential? The change from 900 to 300 is negative 600. Delta V is negative 600 volts. Okay, so let's say that I have a bunch of charges. You know, instead of just having one charge, let's say that I had 2 charges. Or maybe I even had 3 charges. Heck, maybe I had 1,428 charges. You know what? I can calculate the potential due to that arrangement by simply finding the potential due to each one of those and then adding them up. And that's all that this slide says. It looks a little bit scary. Students sometimes get intimidated by the summation notation. But heck, all this means is that if you've got multiple point charges, you simply take the sum of the potentials of all of those charges and add them up. Now maybe that seems obvious, but you know, we don't just add the charges, for example, and then calculate the voltage from that. No, what we'd have to do is we have to add the voltage, right? So we find the potential due to each charge, and then we add them up. We don't add the charges, we don't add the distances, right? So there's other ways you might conceivably imagine you would do this, but we don't do that, right? The law of superposition says we find the potential due to each charge and add it up. And we do that with electric fields too. But the nice thing about with potentials, again, it's not a vector, so man, we just straight up add them up. I'll show you what I mean. Let's do a quick example. Here we have a dipole, and so if we had just the negative charge, then the entire universe would be at a negative potential. If we had just the positive, then the entire universe would be at a positive potential. But if I combine the potential from the positive and the potential from the negative, then we get half of the universe that's negative and half of the universe that's positive. And at the midpoint, right in between the 2 charges, the potential will always be 0. Again, the potential is simply the potential due to this charge plus the potential due to this charge. Either one of those is a straightforward calculation, which means that even for a complicated situation, we can still find the potential in a fairly straightforward fashion. Here's a numerical example to show you what I'm talking about. What is the electric potential at the point indicated in the figure? Now it's important to realize that there's not a charge at this black dot. It's just a point in space. I could have asked you about the potential here, here, right here, over there, right? But I didn't. I asked you for the potential right here. There's no charge there. That's okay. There's still potential, even though there's not a charge there, to experience potential energy. So we'll draw the situation, and then we'll simply find the potentials to each one and add them up. Okay, so now I've sketched the situation here. We're trying to find the potential at this point right here. we're going to use this equation, but we're going to apply this equation to find the potential at this point for this charge and this charge. Let's see how that works. So we know that the total potential will simply be the sum of the potential due to charge 1 plus the potential due to charge 2. Now let's call this charge number 1, and let's call this charge number 2. Okay, well, let's go ahead and plug in some letters here. I like to factor and do all my algebra with letters that I can before I plug in numbers. Let's do that. Now I can plug in numbers. And remember, we're going to use our signs. So this is a negative 1 times 10 to the negative 9th coulombs over R1. Now remember, R is always the distance from the point of interest to the charge. From the point of interest to the charge, for charge 1, it's 4 centimeters. Again, including the sign of our charge, 2 nanocoulombs. How far is it from charge 2 to the point of interest? 5 centimeters. And we run our calculator, and we get 135 volts. Okay, not too bad. Now, the nice thing about this, right, is, I mean, even if I gave you like 5 charges, it would take you longer, but it wouldn't be harder, right? I mean, yeah, you'd have to add up 5 things instead of 2 things, but it's not any harder, right? It's just longer. It's more complicated, but that's different from being trickier or more difficult. So, anyhow, potential is a very powerful idea.